Right, so I started the recording. Okay, Tiffany, I'm going to turn it over to you.
Awesome. Cool. Thank you so much. I'm really excited to be chatting about astronomy and the universe with all of us. And so what I'm going to do is lead us through a presentation about astronomy and space. And then what I hope is that we can spend a few minutes maybe at the end kind of on an online activity where you can color some space photos yourself. And we'll have the link available for you as well. If you need to do that after the session, that's fine too. And throughout the session, I am the type that really likes to answer questions. And so if you think of a question while I am talking, you can, if you've got the option, I'm not sure if everybody does, but if you've got the option, you can raise your little hand on Zoom. So you can go to reactions and raise hand, and it should pop up the hand in the corner there. Or if you type a message into the Zoom chat, I'll try to keep an eye on that as well. And if I can answer your question at the time, amazing, I will. And if it's something that I need to answer at the end, I'll just let you know to remind me at the very end, and then we can talk about it. So I am going to try to share a presentation here. So let's see if I can get that pulled up. Actually, I just want to make sure that I've got it so it'll be smooth. Maybe, and let's play. Okay, thumbs up if we can see that okay. Amazing, thank you. Excellent. So welcome, I'm excited to be here. This is Coloring Our Universe. So I am an astronomy instructor at Washtenaw Community College, and I'm excited to be sharing astronomy with us here. So when we look at images from telescopes, images that might be either in books or online, they're often these absolutely beautiful images full of color, full of wonder, but really it's a combination of science and art to get these lovely images. So hopefully by the end of the session, we will see how to create some images like this one here. So let's get started. So this is a photo of me. This is me using a telescope. This is at a telescope in Canada, actually. It's called the Burke-Gaffney Observatory, but we can see how big that telescope is, and the place where you would look through is where my hands are. And so I'm going to take this moment as well to say that I hope that you get a chance to visit the Detroit Observatory at some time in the future. They do public sessions where you can go see their observatory space. And I think that there's one happening near the end of the month, near the end of August. So maybe make a note to yourself, you'll have to check that out in the future. So we use telescopes. I have used telescopes in the past. And like I mentioned, I teach astronomy at Washtenaw Community College. So today's plan, we are going to introduce astronomy. We are going to introduce telescopes. I am going to talk then about the electromagnetic spectrum and what that means. And then we'll look at some black and white images, see how they get combined. And then we will do that do-it-yourself activity, that astronomy in color activity. Hopefully you'll get to make some images too. And then we'll wrap up. And so let's just kind of get started with astronomy. So space is huge. There's so much stuff in space, and there is so much to learn about. Even just this image that we have here, almost every smudge of light in this image on this slide is a whole galaxy. So we live in the Milky Way galaxy, and the Milky Way galaxy has billions of stars like our sun. So the sun is a star, Earth goes around the sun in our solar system, and the sun is just one of billions of stars in our galaxy. And then in the whole universe, there are billions of galaxies. It's huge, it's so big. So I've talked a little bit about things in astronomy, but what is astronomy? So this definition here, it's a branch of science. It deals with celestial objects, deals with space and the physical universe as a whole. So when we are talking about astronomy as a science, it's the study of space and stuff in space, and then space as a whole too. So an astronomer would be a person that does astronomy, or maybe a student in astronomy can also be called an astronomer. So we are all going to be astronomers today. And in astronomy, out in space, there's a lot of different types of objects. And so we have photos of a lot of these objects. There is a photo of Jupiter, and right next to Jupiter, there is a little dot that is one of its moons called Europa. We have images of clouds of gas and dust up in the sky. So this is an image of a nebula. It's called the Stingray Nebula. And it's just a bunch of cloud or a bunch of gas and dust, sort of like the clouds that we have in our atmosphere. We've also got clusters of stars. So this is a globular cluster. It is a spot in space. It's an object in space where there are hundreds of thousands of stars, just like all clumped together in like a sphere. So like a ball of stars. And then we have things like whole galaxies. We saw this photo in one of the last slides. This is a galaxy, kind of like our own Milky Way galaxy. And we have these incredible photos of these huge objects out in space. So astronomy is really full of these beautiful, colorful photos. And the question that we're asking ourselves is, how do we get these photos? So let's see how that happens. So we can do astronomy by just looking up towards the sky with our eyes. And maybe if the skies are clear tonight, we can go outside, look up at the sky, and this is something that we might see just with our eyes. We can see the horizon down at the bottom, stars up in the sky, some bright objects. But if we were to use something like a telescope, we could zoom in to just one part of the sky to help those distant objects come into view. So if we zoom in, maybe we see now that moon come into view, where that green circle is what we would see through the telescope. So before, the moon just looked like a tiny little dot, but with a telescope, we can zoom in, bring that light closer to us to see more of the detail. So if we were able to go outside tonight, look up at a clear, dark sky, late at night tonight, you might be able to see the moon look just like this. So we use telescopes in astronomy to help us study the universe. So telescopes really are like a giant light bucket. They're like big buckets for light. So the bigger the telescope, the bigger the bucket, the more light that we can collect from a distant object in the universe. So telescopes can either have lenses, like our eyes have lenses to bring light to a focus so that we can see it, or maybe they have mirrors. Lots of types of telescopes have mirrors to bring the light in from the universe. It bounces off the mirror. Maybe there's a couple mirrors that it bounces off of, but it just gets focused onto a place where we can either put our eyeball or put a camera so that we can see those objects. And so if we just look at the telescope on the right, or to take a step back, both of these images, the left image and the right image, both show different types of telescopes. So these are smaller telescopes on the left. On the right is a bigger sort of telescope. And we can use these telescopes to look out into the universe, or telescopes like these. And so if we look at the telescope on the right, we're going to see some arrows, and that's showing that the light can come in from the universe. It's going to hit the mirror that is at the back of that telescope at the very bottom. It's going to hit that mirror, bounce back to a second mirror, and then bounce down through the middle of the telescope to where a camera is going to pick up that light. So on the backs of telescopes, we often have cameras to take photos of what they see in the sky. There's also telescopes out in space. Has anybody heard of the Hubble Space Telescope? If you want to just, yeah, I've got a hand raised there. Amazing. Maybe thumbs up, thumbs down. I've got some thumbs up. Amazing. Have we heard of the James Webb Space Telescope? Some thumbs up, thumbs down. Have we ever heard of it? Some thumbs there. Nice. So these are telescopes that are out in space that have allowed us to see objects in the distant universe. And remember, I said telescopes are kind of like buckets for light, where the bigger the telescope, the more light that we can collect from the universe. And so if I zoom into just the mirror sizes of these telescopes, we can see how big they are. So Hubble is down on the left, and there's a person, there's an image of a person there next to the mirror. So this donut shape behind the person is the mirror on Hubble. And you can see how big it is. It's like 2.5 meters. That's something like 8 feet across. Whereas the James Webb Space Telescope on the right, you can see how huge the James Webb Space Telescope mirror is, especially compared to the person that's standing right in front of it. So Hubble has been in space for about 30 years. It was launched in 1990 and has been taking photos of space for us since then. And so the Hubble Space Telescope is about the size of a school bus, and it's been taking lots of photos for us. And the James Webb Space Telescope was just launched last Christmas. It was a really big news story in December that you might have heard about at the time. But what's really special is that it just started to we just started to get the first images from James Webb just last month. So James Webb has been in the news in the last month or so too. And so Webb is like the size of a tennis court. It's really, really big, and I'm really excited. Maybe I'm biased, but I'm really excited to see what Webb is going to be giving us in the future. So these are some telescopes that are out in space, taking photos of the universe for us. So we can use both our eyes and telescopes to do astronomy, but often it's the telescopes that we use to take photos of objects that are in space. So let's think about what we need in order to capture a picture. Usually, when you're capturing a picture, even with something like a cell phone, you need an area that is lit up. If it's fully dark, you can't see anything, so we need light in order to take a picture. But there's actually lots of different types of light. And this is a huge image here, but I want to talk about this image because when we take pictures of objects in space, we need to think about the color that we're seeing a little bit differently. So this is the full electromagnetic spectrum. It goes from radio waves to gamma waves or gamma rays. And we can see that starting on the left side of the image here. These are all different kinds of light, just like the visible light that we see with our eyes. But some of it has really long wavelengths. The wavelengths are really long, and those would be things like radio. So the radio that you hear in your car is actually a light wave traveling to your car, and then the radio box, the computer in the radio box converts that to sound for us so that our ears can pick it up. But it's actually a light wave traveling to us with a really long wavelength. But it's light that our eyes can't see. So that's really long wavelengths, and really short wavelengths would be things like X-rays, gamma rays, ultraviolet radiation, the stuff that gives you a sunburn from the sun. That's also stuff that our eyes can't see. And so the full electromagnetic spectrum from radio to gamma rays, it's all different types of light, from very, very long wavelengths to very, very, very short. But the part that we can see with our eyes, the visible light, is actually a really small part of this whole spectrum. And so our eyes are fine-tuned to see the light that is mostly given off by our sun. That makes sense, right? We have the sun producing light in our solar system. Earth is around the sun. All of our daylight comes from the sun. So our eyes have been evolved to see that visible light really well. But that means there's so many other different types of lights that we can't see with our eyes. You might notice that there's a microwave oven down here. Your microwave actually produces microwave light, and it's got a wavelength of about 5 or so inches. It's about 12 centimeters. And that's just a different type of light. So the part that our eyes see is a really small part of this. The Hubble Space Telescope can see what our eyes see, but it also sees a little bit beyond the red and a little bit beyond the blue. So beyond the red, we call infrared. Beyond the blue or beyond the purple, we call ultraviolet. And then Webb the James Webb Space Telescope, sees only in infrared, and our eyes can't even see that. So this telescope is out in space looking at things that our eyes cannot even see. And so we'll come back to how we get colorful images from Webb, even though it looks at something that our eyes can't see. And we'll see how that works. And there's so many different types of scientific instruments, these telescopes, all over the world and up in space to capture the different kinds of light. And so you'll notice the spectrum of light is actually flipped around, where radio is over on the right now, and the short wavelength gamma rays and such are over on the left. But we have all of these different instruments that are named, and these are just a few of the different types of telescopes. So astronomers and scientists can actually learn different things about objects in the universe depending on the wavelength that we look at them in. So NuSTAR is a telescope in space looking mostly at like X-rays. There's a telescope that exists on an airplane, and so we fly an airplane into the atmosphere to look into the infrared. There's lots of telescopes on the ground. There's some that are looking at the microwave and radio wavelengths. And then we see Hubble up here looking a little bit above visible, and just to the left and right of visible too. So there's lots of stuff for astronomers to take photos of the universe. But when we get those photos, we have to think about what we actually see, because there's that entire spectrum of light. And our eyes and then individual telescopes only see parts of that spectrum at a time. So here's the thing. When we use telescopes to take pictures, they only see a small part of that full spectrum at a time. And astronomers, when they tell a telescope to take a photo, astronomers know that specific wavelength that the telescope is taking a photo of. So the image that we get, the data that we get from telescopes when they take images, it's just black and white. It's just a black and white photo. We can add color later if we want. So this image here, it's a monochromatic image. So monochromatic means one color, which just means it's black and white. And this is an image of a galaxy. So this was taken from a robotic telescope up in Canada that I was able to get an image from. And this is a spiral galaxy like our Milky Way, but notice it is just black and white. And this is really useful to astronomers because this black and white image, it just tells us how much brightness we got at each part of the camera. So if something is really white and really bright, it means that there was a lot of light hitting that specific part of the camera. If something is black, then there wasn't any light hitting that specific part of the camera. And how bright something is can tell astronomers a lot about that object. So when astronomers need data from telescopes, they just need a black and white image. But that's not really quite as fun as taking a full color image and having that beautiful full color image. So this is really where not the magic, but the science and art happens. So we can take those black and white images and turn them into color images. And this is the process. So to turn an image into color, we take 3 different images. We could take more, but we've got to take at least 3. And what we do with telescopes is generally they would take a photo of just a small piece of wavelengths, just a little piece of light. And sometimes it's because the camera only sees small pieces of light, or sometimes what we do is we put a filter in front of the camera, kind of like sunglasses for the telescope. So I could take one image with a red filter in front of the camera, another image with a green filter, and another image with a blue filter. And then what we do is we just add those 3 images together. So we get black and white images from all 3 of those different filters that we took. So I'm going to go back to this slide here. Red, green, and blue. We get those black and white images because the telescope only gives us black and white images. But then what we can do is we can go to your favorite photo editing program, say something like Photoshop, or even if you are using something like Canva, you can add different like colors to different images and then just layer them on top of each other to add them together. And that's where the color photos come from. And like, that's how that works at the most basic level. And so we take these images, these science images, we get this data in these black and white images, and then we can combine them in maybe whatever artistic way we want to. So the individuals that work at, say, NASA, that take data from a telescope like Hubble, they get the black and white images, and then they decide, okay, how are we going to combine these to get a beautiful color image? And their priority is to preserve the science that is happening in there. They want to make sure that they actually represent what is happening in the universe, but they also want to pull out the color so that we, with our eyes that see invisible wavelengths, can appreciate them. So that's one object, and we can look at another object. So we would take one image in red, green, and blue with those filters, kind of like a sunglass, and then combine them. And if we did, maybe we would get something like this. And you see that green line actually across the image? When this telescope was taking this photo, there actually happened to be a satellite go across the image to cause that line, but it only happened in the green image. So now that satellite line looks like just a green line. But you can see how we add those colors together to get this colorful photo. And this is really how pretty much all other cameras work, like our cell phones. They work this way, but it's kind of all done automatically in the background. And Colby asked in the chat, could this be an effective way to get all of the colors of the moon? I'm going to answer that in two ways. One, yes, absolutely. But two, the moon is very gray. Like, there's not a lot of color on the moon. So absolutely, that's how we can get color photos of the moon, of anything. But the moon is actually very gray. But you could take some artistic direction and say, oh, I'm going to take an image in the red filter and make that part of my final image like really strong. So the moon looks kind of red. So you can have a little bit of artistic liberty with that. But absolutely, I like that question. And so the images that I have up on the screen here, the left one really is a close-up view of what a cell phone camera sensor would look like. And you can actually see like those red, blue, and green dots, like if you look really closely. On that sensor, there are already those red, green, and blue filters. And so your cameras, like a cell phone camera, takes a photo, and what it's really doing in the background with the computer software that's running it is it's taking kind of like black and white images and assigning different colors to them and combining them so that we get a color image out. And that's how that works. So it's like how telescopes take images, except it does a whole bunch of automatic stuff with the computer so that we can get a color image automatically. So we mentioned, or I mentioned earlier, the James Webb Space Telescope takes images in infrared light, and our eyes cannot see infrared light. So what happens when a telescope looks at light that our eyes cannot see? We might get something like these 5 different black and white images here. The left one, the leftmost one, is a radio image. So it's an image from radio wavelengths, and then infrared, and then visible, like our eyes would see. And then ultraviolet. Ultraviolet is like the light that burns our skin with sunburns. And then X-ray. And that's the same type of X-rays that you might get like at the dentist when they want to take an image of your teeth. So telescopes can be built to look at all of these different wavelengths. And we can assign different colors to each one of these, kind of however we would want to, however we think would pull out the image the best. And I want to take a moment kind of to step back here as well, because all 5 of these images are looking at the same object in space. This is called the Crab Nebula. So this is a nebula. It's a cloud of gas and dust up in the sky. And so this cloud of gas and dust looks different depending on how we look at it. So this Crab Nebula, it's what we call a supernova remnant, and it's the leftover debris after a star exploded at the end of its life. And so something that I think is really interesting about the Crab Nebula is that Chinese astronomers 1,000 years ago actually saw this explode. It was really, really bright in the sky. It would have been just as bright as the full moon is in our sky for a couple of months, and then it would have dimmed again when it exploded, and then that explosion kind of died off. And so we actually see different parts of the object up in the sky when we look, say, in radio compared to X-ray. And there was a question in the chat, why are there no gamma wave photos? And there are gamma ray telescopes out in the sky. So there are some objects where we have images in the really short wavelengths that gamma rays are. And then maybe there's other objects that just aren't very interesting, because gamma rays, going from the question that we had there, gamma rays come from regions in space that have a lot of energy, that are just extremely hot. Usually, those are from near the centers of galaxies. And at the center of every galaxy, we think, is a supermassive black hole. So generally, those most energetic wavelengths, like gamma rays, come from around places where there are supermassive black holes. And there was another really good question in the chat that I'm going to answer here too. So we had, how long is a lifespan of a star? And I really like that question because we're looking here at the remnants of a dead star in this object. And so stars can live for a variety of lengths, and it all depends on how big they are, how heavy they are. So a star like our sun, its full lifetime is about 10 billion years. So that's like double the age of the Earth right now. For stars that are really, really, really heavy, so say 30 times as heavy as our sun, they might only live for maybe 100 million years. So like 1/10 or 1/100th of the lifespan of our star. So it all depends on how heavy they are. The heaviest stars live the shortest lifetimes, and the lightest stars, or maybe like the smallest stars, live the longest lifetimes. And yeah, another question that I'm going to answer, because we're kind of talking about stars now, and then I'm going to go to the next slide. Liliana in the chat asked, what's the range of how big a star can be to how small a star can be? I love that. The lower limit of how big stars can be, so like the smallest star, would be probably a couple of times bigger than our planet Jupiter. So Jupiter is the largest planet in our solar system. It is a gas giant. And if you get, I think it's 8 to 10 times as big as Jupiter, that is the smallest size that a star can be. And what makes a star is if it is fusing hydrogen into helium in the center. So that's what our star, the sun, is doing. It's fusing hydrogen into helium in the center. That's what makes, that is what allows it to give off light. That is what is running the star. The biggest stars, ooh, they're very large. I would say maybe like 100 times as big as our sun, because there's this balance that stars have. Stars have essentially nuclear explosions happening in their centers constantly. That's what powers a star. That's what gives us light from the star. But also there's gravity. And gravity is the stuff that keeps us here on Earth. It's keeping me sitting in my chair instead of floating away. But in a star, the gravity pulls all of the layers down towards the center. So there's a balance between all of the nuclear explosions that are happening at the center and pushing things outwards, and gravity pulling things inwards. So if you get too big, then the gravity for the outermost layers is not very strong. And those outermost layers just kind of like puff away into space forever. So if you get too big, a lot of your star actually just kind of floats away because the gravity out there is very weak. So we are talking about this Crab Nebula. I told us that it was a supernova remnant, and we are seeing how when we look at different parts of light, from radio to infrared, visible, ultraviolet, and X-ray, we can actually see different things in the same object. So it's been beneficial for astronomers to have telescopes that see different things or different pieces of light. And the reason that I got to this slide in the first place is we were thinking about what happens when a telescope observes light that our eyes can't see. And we decided, well, you know, we have black and white images. We get black and white images from telescopes. Why not just assign colors that we can see to each of these images? Like putting a filter over it saying, hey, radio, I want you to be colored red. And then we can combine those to get a color image, just like all of the other beautiful images that we see from objects out in space. So I'm going to leave this end result as a challenge to you, because the next thing that I want to say is that we can try this for ourselves. So we can use a tool that's available online from the National Radio Astronomy Observatory called Cosmic Coloring Compositor. It's hard to say 3 times fast, but this is available on a website. And maybe if one of the moderators, the other individuals leading this Zoom call, maybe if we could just get that into the chat so that we can link it, that would be excellent. And I can help us with that if needed, just let me know. Because when we visit this website, we can actually do this ourselves. And yeah, we got it in the chat there, amazing. And you can, if you want to right now, I know that not all computers can handle doing multiple things at once. So even if you just want to jot it down on a Post-it note, totally fine, because you can see how I do it too here in a second. So I'm going to go to the next slide, but this website is going to stay at the top just in case you want to go there. So this is how we can actually try this for ourselves. And I'm going to go through how it works, and then I will share my screen just kind of as a demo here. So the first thing that we would do is choose an object that we wanted to try. And the first one that they've got on the list is the Crab Nebula, like we were just looking at there. So we can choose an object to start, and you'll just click select image. And then we turn on the desired wavelengths. So different objects have different images in different wavelengths. The Crab Nebula happens to have these 5 different images. So you can turn those on or off when you're playing with it. And then you can choose a color for each wavelength. So you can pick which color you want each wavelength to be represented with. Something else that we can do is adjust the brightness of each of those wavelengths to bring out the different details, whatever you think looks most interesting. And then you can just save the image, have it for yourself, make it your new desktop wallpaper, whatever you would want to do. So I am going to try to share what it looks like on my end here. So hopefully we can see this here. So this is what the website looks like. It's called Cosmic Coloring Compositor. And if I scroll down, this is the website that we get, like I was just showing us, and we can pick different images or different objects here. So maybe I'll pick the Whirlpool Galaxy. Actually, maybe I'll stick with the Crab Nebula because we just saw it. I'll let everybody else choose different images. And then I would hit select image and it'll pull up for me. It reloads the page when you hit select image. So there we go. And then I can turn on or off each of these different wavelengths. So maybe I don't want any radio, I'm going to turn that one off. Maybe I don't want any X-ray, I'll turn that one off for now. And we can pick different colors for each one of these to be and change their brightness. And so what I would love us to do is, if you have the ability to pull this up on your computer, to just spend a couple of minutes seeing what images you can make, because now you are working like the astronomers that create these beautiful color images. And I want to give us a couple of minutes to do that. So if there are any other questions, this would be a really good time. And then I've just got, I think, 2 more slides to go over after. So I'm gonna maybe give us like 3 or so minutes if you want to play with this on your own. And if you've got any questions, this would be a good time to put them in the chat, or you can speak on Zoom. Otherwise, I can keep talking about space. Something that I'll mention is a criticism that I often see about space images is maybe there will be a new image released from NASA, but a bunch of people on the internet say, oh, that's fake, it's not real, it's a fake image. And they're right, a little bit. It's a real image of a real object, but the colors are kind of fake. It doesn't mean that it's less value. We just have to understand that there are some wavelengths of light that our eyes can't see. So we've got to give them different colors so that our eyes can see it properly. Is anybody trying it and wants to like kind of share what you're seeing? I see a thumbs up. Or if you want to tell me like which object you picked and kind of how the different colors look. And if you don't want to share, that's also fine. I was pretty excited when I found this tool online because I think it makes creating your own space images pretty easy. And then if you wanted to get even further into this, there's a lot of data from a whole bunch of telescopes that's just publicly available that you can like download and try yourself. And Liliana, I've seen the camera there. Did we have a question that you wanted to ask?
How can you send it to the chat?
I noticed that you just unmuted and I didn't quite catch your question there.
How can we share what we made?
It's a good question. I'm not sure.
Actually, I could make her a co-host for a moment.
Yeah, and just make sure that you only share like the image that you're trying to, just be careful of what you're sharing, I guess is what I'm trying to say. But absolutely, I would love to see it.
All right, hold on.
Let me stop.
Liliana, I'll see if I can do this for you. And then you just choose share screen, okay, Liliana?
Amazing.
Okay. All right, you want to try it?
No way.
Wow.
Oh, that's really nice. I love the like pastel sorts of colors. And this was of the Crab Nebula, right? That's really cool. Nice color choices. I like how you chose really like vivid colors and it turned into something that looks like kind of soft and nice and pastel-y. That's really cool. And then there was a question in the chat from Linda too that I want to answer. Astronomers totally use the multicolored composite images too. So astronomers, well, mostly use the data from those black and white images, but when you combine information from multiple wavelengths, it tells a different part of the story. So seeing all of those colors together can kind of help put the whole picture together, even though astronomy research sometimes focuses on just one wavelength at a time. But absolutely, yeah. Yeah, thanks. I'm going to go back to sharing my PowerPoint here because I've just got a couple of slides left and I am super excited about the things that we were able to share. And I hope that maybe you take some time too in the future to just play around with it and see what you can create. And I had started to mention before too, there is so much publicly available data from these big telescopes. Like there is data available from the James Webb Space Telescope where you can go download the black and white images and toss them together in your favorite photo editing program and make color images on your own. There's a lot of opportunity here to combine that science from the astronomical images and how you might want to artistically combine them together. So these were some images that I made. So I had a photo in the top of the Crab Nebula, that was M1, and then M51 is the Whirlpool galaxy in the middle, and then this crazy image of the Milky Way center. It just looks kind of spooky, I think. But these were some of the images that I made there. And so to wrap up this session, and I'm happy to take any questions here, but I just kind of want to go over some of the things that we talked about. So astronomy in general, it's the study of the universe around us. So we can do astronomy with our eyes by looking up into space, looking at the nighttime sky, but also with telescopes that are on the ground or telescopes in space. And so we've been able to learn that telescopes actually take images in black and white, and it takes a combination of art and science to create those color photos. So this animated, I'm going to just call it an animation. Here on the slide, you can actually see data from the James Webb Telescope turning from black and white into that color image. So, final thing, I am Tiffany Fields, an astronomy instructor at WCC, so Washtenaw Community College. You can find me on email if you've got any questions or want to share the cool things that you made. And I am just super excited that you were here so that I could share this with you. And so hopefully you can go and make astronomy images on your own as well. And I'm super happy to take any questions that we've got. Thank you for the thumbs. I love it.
Thank you so much, Tiffany. This was marvelous.
Thank you. And you're welcome.
Thank you. Thank you very much. Very much. Tiffany, do you have an email in case one of our participants has a follow-up question?
Absolutely.
After our session?
Absolutely. My email is on the slide, and I can
that's
also
right.
type it into
Sorry.
the chat here too. I'll
Yeah.
just type it quickly too.
Thank you. Oh, I like that cat.
Amazing.
Excellent. Well, everyone have a nice, wonderful Saturday. And Tiffany, I'll be in touch too about STEAM Week. So everyone
Amazing.
take care and thank you for coming out on a Saturday.
Thank you so much.
Bye.
Hope you have a good rest of your day.
Bye. Bye, Liliana. Okay. All right, we are all